Hey everyone, welcome to E-Day. My name's John. I'm a mechanical engineer at Lockheed Martin and I design parts for airplanes and helicopters. Today I'm going to talk about vibrations and how they affect what I do as a Lockheed Martin engineer. First, we'll talk about waves, wavelength and frequency, and then we'll do a really fun demo with a device called a Chladni plate. And there we can see frequency and resonance and how they affect each other. And then I'll talk about how that affects what I do when I design parts for airplanes and helicopters. So come on, let's get started. Let's talk a little bit about waves, wavelength, and frequency and how they're all related. So first, we'll draw a wave on this line here. And one wavelength looks like this. So one complete wavelength is from here to here. And it includes this peak, and this node here. If we draw a shorter wavelength wave, it will look like this. And its wavelength is from here to here with two peaks and a node here. Now for a standing wave, these two peaks go back and forth like this, and the node never moves. Same for this one, back and forth, and this node never moves. Now remember the term node. This is the point where the wave, or whatever it's going through, is stationary. And here are the peaks, and that's where it's bouncing back and forth. That's called oscillation. Now the other important part of this is frequency. And frequency is the number of waves that can pass in a given amount of time. Usually we measure this as the number of waves that can pass in 1 second, which is called a hertz. So let's say, for example, that from here to here is 1 second. And this green wave has a 1 hertz frequency. So one wave can pass in 1 second. Now this red one, though, has a shorter wavelength, which means it has a higher frequency because we haven't quite gotten to a second. So as you can see, we can get one full wave and then a little bit more, which means this is probably 1.25 hertz or so. So, as the wavelength decreases, the frequency increases, and the other thing that happens is that your node moves. And you'll see this when we demonstrate the Chladni plate. So here's our Chladni plate setup. We've got the plate itself, we've got the frequency driver, and the frequency generator. This is basically a speaker right down in here with a shaft attached to it, and as the speaker vibrates, it drives the shaft up and down. The frequency generator controls how fast this moves up and down. So here we've got everything assembled. We've got some sand on our Chladni plate, we've got the driver plugged in and turned on, and we've got our frequency generator set to 200 hertz. We can adjust this, the amplitude here, or the frequency here. You can see the numbers change when I adjust the frequency. Now as I increase the amplitude, you can start to hear the plate vibrate, and that's resonance. But as we get close to its resonance frequency, you can see the sand start to dance around. And it starts to make these fun shapes. So at 240 hertz, this plate is resonant. But as we increase the frequency, we lose resonance, and it starts to get a little bit quieter. But we keep turning it up, and we get to another resonant frequency. Did you hear that sound get much louder and the pattern starts to change? We can keep going on up to 560 hertz, and the pattern changes again. Let's put some more sand on the plate. You can see that just a small change in the frequency affects the resonance. So let's turn that back down and look at this in a little bit more detail. So here I've turned the frequency down to 560 hertz, and I've turned the amplitude down so you can hear me better. But this is the pattern that it creates. And so what's happening here is the plate moves in different ways. It forces the sand into spots where the plate's not moving. So like here, the plate's not really moving. And this is a node like I talked about earlier on the whiteboard. But this part right here is moving up and down. So you can think about it as the wave is high here and then goes to 0 and then comes back up, and this is at 0 here. And that's what's happening all the way across this in 3 dimensions. So now you can see I've swapped out the square plate for a round one. And the cool thing about this is that you can really see how frequency affects your wavelength. So right now we're at about 70 hertz, but as we turn the frequency up to 110 hertz, we start to see some resonance. And so here's a node, so we've got about a third, 2/3 of a wavelength. But as we go to higher frequencies, let's go up to 430 hertz. You can see we start to see 2 nodes. And that's because the wavelength is getting shorter. It's the same as the whiteboard. Now, as we go up to about 990 hertz, we hit another point of resonance and we get yet another node. And one more, up to 1.82 kilohertz. Now we've got 4 nodes. And you can really see how this plate is moving up and down here, 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 and here. But where the sand is, the plate's not moving. And so it's like a ripple in a pond moving up and down as this thing shakes.
So what does all this have to do with my job as an engineer designing airplane and helicopter parts? Well, let's go back to the Chladni plate for a minute. Remember the frequency driver, the speaker with the shaft connected to it? The frequency driver uses the vibrations from the speaker to generate the vibrations that move the sand on the Chladni plate. Now remember how the sand moved at some frequencies but not others? Well, that's because the frequencies where the sand moves are resonant frequencies. That means that rather than the plate absorbing the vibrations, the plate actually amplifies the vibration when it's at those resonant frequencies. In a helicopter, the big vibration generator is the main rotor blades. And that's these big blades on the top here. They spin at a certain speed, and every time the tip of one of those blades goes by, it creates an impulse or a shake on the helicopter. All of those shakes combined create a constant vibration at what is called the blade pass frequency. If we make parts for the helicopter that are resonant at the blade pass frequency, they can make the vibrations much worse because they amplify rather than absorb the vibrations. This can cause parts of the helicopter to wear out very quickly or even break, so it's important that we make sure that our parts are not resonant at the blade pass frequency. Well, that's it for our Chladni plate and vibrations video. I hope you learned a little about vibrations, frequency, and resonance. Thanks for watching, and enjoy the rest of your E-Day.
At Lockheed Martin, we're on a mission. Your mission. When millions of people are counting on you, you can count on us. To build the impossible, to invent the inconceivable, and solve every problem with speed and reliability. Every mission is an expedition of the greatest importance, both to you and to us.